Okay, today we're going to look at hypothesis testing for two independent means. So pretty much we're picking two random samples from two different populations. Okay, just something to note, the two samples do not have to be the same size. So up here I kind of just have a summary of what the two different sampling distributions may look like. So right here I have a description of the phantoms. You can see we're looking at the difference between the population. So obviously your null is going to be that there's no difference. You may see it written like this. More commonly, I'm going to write my null hypothesis like this. But either way is acceptable. It's important you know that your null equals 0 because generally in your test statistic, which comes down here, this is going to disappear because you know that you're assuming if there's no difference, that's going to be 0. Okay? Then your alternative is going to be there is a difference. If there is a difference, it's not going to equal 0. Also, that difference could be greater than 0. Okay? Or it could be less than 0. And just looking right there, let's go ahead and fix. Okay, we've got that, and then we have it also less than 0. But again, other than this right here, and this right here are more commonly how I'm going to write my hypothesis. Now let's look at our assumptions. Okay, for your assumptions, you have the random conditions. Okay, for the random conditions, you're going to either have a random sample, or if it's an experiment, you're going to have the random allocation to treatment groups. Okay, so just know that most of the time you're going to have your random samples, but if there was an experiment, your randomization comes when there's random allocation to treatment groups, so watch for that. You're going to have your 10% condition. That's for samples. That's for both groups. Notice that's for samples alone. And then your nearly normal condition, that's either going to come by making histograms. Those could either be box plots. If you'd rather, we've done box plots before. Or by applying the central limit theorem. Okay, we have our test statistic here. This is going to be 0. You're going to get this from your calculator. Know in your AP formula sheet is statistic minus parameter divided by the standard error statistic, and you can get that right from your formula sheet. You're going to calculate that test statistic, that's your T. Your O is your observed p-value. Okay, this is all the same as before. M is you're going to make decision. A small p-value means stronger the case against the null, and then you're going to do your summary. Okay, so a lot of this is going to seem familiar. And then I'm going to kind of quickly go over the panic. Okay, P again, you're going to describe the two populations. You have to describe them both in context. Your A, your assumptions are going to be the same. You can see A, you're going to do the difference. You're going to get your T critical value, and then go from here as far as your standard error, give your interval, and then do your conclusion like you did before. So let's go ahead and do one of these. Okay. It says a claim is made that the mean price for a certain drug, privately owned drugstores, is greater than the mean price for the same drug at stores that are part of large chains. Let A denote the population of privately owned drugstores and B the population of chain drugstores. A random sample of 10 private stores revealed the mean price is $8.75 with a standard deviation of $1.15. And a random sample of 14 chain drugstores revealed the mean price of $7.97 with a standard deviation of 95 cents. Okay, we're going to perform a hypothesis test at a significance level of 2.5% to determine whether there is statistical evidence exists to support this claim. Okay, so the first thing we need to do is go through and identify each of these. Okay, so for A, it says to you A. I could also use like P for private and C for chain. I actually do that a lot, but since it says let A denote and B denote, I'll do that. But generally, I would have done P for private and C for chain here. So A is going to be the true mean price for a certain drug at privately owned stores. Okay, and then for B, again here, this would have been P and C. I am in favor of little ditto marks in this, so true mean price for a certain drug. And I'm going to just change this to at chain stores. Okay, so I went ahead and I determined specifically what the populations are in this case. So for H, right here you can say greater than. So they're saying that private is greater than chain. So A was private and chain. So my HO in this case, they're saying that's always going to be equal to, not equal to. But then my HA, then A, be equal to. Okay, we're going to go on and in this case go through our assumptions. You can see that I went ahead and switched the numbers up there. I realized for the purpose of this problem it'll make it a little easier. So for our assumptions, okay, we have to have our random conditions, right? So we're going to have a random selection of 30 prices from private stores and then we're going to have a random selection of 34 prices from chain stores. Okay, so there's our random allocation there. Okay, so we've got that. So then let's go on to our 10% condition. So we're going to say 10%. It's safe to assume there are more than 300 prices at privately owned stores and 340 prices at chain stores. And if you think of all of the different stores, that's a safe assumption. And then for our last thing, we're going to go with our nearly normal condition. We can say 30 is greater than 30. 34 is greater than 30. The central limit theorem applies. And you know I like to say normality is plausible. Or you could say it's safe to assume it's possible that they're normal. Something along those lines. Let me move that up so you can see it. Okay, so we're on to naming our test. Okay, to me again, you know the best way to name it is always just to give the formula. T, means are always T. this over standard error statistic. Remember, you can get this from that formula sheet. Here you're just kind of pooling those variances. This is stuff we learned early in the year, if you think about it. So let's go ahead and plug this in. So I had $8, so T equals, okay, you do want to put that T equals in. Do not forget that when you're doing this. $8.75 minus $7.79 over the square root of 1.15 squared divided by 30 plus 0.95 squared over 34. Okay, let your calculator do this calculation for you. You're going to go to Stat. I'm going to try and get that out of, over to Calculate. You're going to go to Two Sample T-Test. I have stats. I put them in. Okay, so my first mean is 8.75 with the standard deviation of 1.15. That's 30. My second mean is 7.97, 0.95, and that's 34. I'm choosing greater than. You always choose no to pooling, just so you know, say no to pooling. Okay, so I have a test statistic of 2.93. You do need to write that down. Okay, mine's kind of small because I'm running out of space. Write down your test statistic. Now, you see I have a very small p-value. That is a strong case against the null. So my p-value is right there. So 0.002, we're going to say that's less than 0.05, so we would reject. Okay, you don't really need that in this case, or, I'm sorry, 0.025, they gave us 1. If they did not give us a significance level, we would use 0.05 as default, but if you need that in your head. But just know that a really small p-value is a very strong case against the null. That's something that's very important to understand. Okay, so we can say at 2.5% significance level, there is enough evidence to reject HO and support the claim. That the mean price for a certain drug is higher at privately owned stores than chain stores.